Students, welcome to this lecture in which we're going to talk about some applications of surface integrals. And first we're going to start with the flux, but we need some preliminary discussion before we actually define the flux. So first thing we're going to talk about is orientable surfaces. We say that a surface S is orientable. Some people call it two-sided. If it is possible to define a unit normal vector n, define a unit normal vector n at each point x, y, and z, not on a boundary of the surface. And also we will require that this function n, which is a function because you define it at every point, is continuous. And n itself is a continuous function. Of x, y, and z. So in this case, this surface S has two identifiable sides. Usually a top and a bottom, or inside and outside, for example. But you can definitely see these two sides, or inside and inside and outside. So that means we can choose the normal vector. We can choose the normal vector. So once we choose a consistent direction for all normal vectors to a point, we call the surface oriented. We call the surface oriented. So basically we choose a direction, and if we can choose a direction, then we can call the surface oriented. Right. So let's look at small example. if we think about a sphere, is a two-sided surface. Why? Because it has inside and outside, right? It has an inside and an outside surfaces. And we have to notice that we can't move from the inside to the outside on the surface without passing through the sphere, without passing through the sphere. All right. And this is an important notice, we'll discuss it in a second. Then the positive orientation for the sphere or for any closed surface is to choose outward normal vector. There are a lot of them, so in plural. So basically what we mean normal vectors pointing out or pointing away from the center. Away from the interior, that's a better word. So most of the surfaces that you will see are two-sided, and the most famous example of one-sided surface is a Möbius strip. So one-sided example of a one-sided surface. And the most famous one is the Möbius strip. So basically, I found one on the web. So if you think about Möbius strip, you can construct a Möbius strip by taking a strip and then cutting it off and flip it and connecting the sides. And this is the Möbius strip. So basically, if you're standing over here, you see you can move around, and you can move around, and you come to the other. There's just one side pretty much, and you will flow on the other side, and then you come back to the same point without going over, right? So this has only one side. We're not going to see them often, but why people split them up into two kinds? That's the example of the other kind. So why do we need to orient the surface? That's the question. Why do we create oriented surfaces? Just to talk about flux. So what is a flux? Flux is how we're going to define the flux. It is easiest to visualize the flux for a vector field representing the velocity field or some charge field, but we'll talk about fluid motion, but you can think of it as an electric charge field if you want. So the velocity field for a fluid motion. Fluid in motion. So if you have a fluid that's moving, then the flux measures the net flow rate of the fluid across the surface. So basically it's a difference the net difference of the fluid flow. And this is a net flow, but if it's a net flow, it has to have a direction, right? You know, the fluid has to flow somewhere. So we have to add this to our definition across the fluid across the surface, and we're going to add in the direction of the specified normal vector. And since we have a lot of them, let's put it in plural. And for this to make sense, the surface has to have two sides, right? So if we notice here, a little notice here, that for this to make sense, the surface must be or must have two identifiable sides. That's a better statement. So that means surface must be orientable. Surface must be orientable. So let's put all of this together and create the following definition. Let f of x, y, and z be a continuous vector field defined on an orientable surface S, orientable surface S with unit normal vector n, and we say that the surface integral of f over s but that's basically, we can think of it as the flux of f over s, you can think of it as a flux, is given by the integral over s of f dot n ds. All right, so a couple of things to add to this definition is, let's put it as a note. So what is the note? Since n is a unit vector, the term inside of this integral, or the integrand f dot n gives at any point on S the component of f, in the direction of n. If you remember the beginning of the semester, that product does it, right? So it creates what portion of f goes along the n, right? But this means if f represents the velocity field or the charge or electric field, right, for a fluid motion, that's what we're discussing right now, but it can be applied in different areas of physics, then f dot n corresponds to the component of the velocity that moves the fluid across the surface. From one side to another. Right, that's one thing to notice. Another thing to notice that direction. So note that f dot n can be positive or negative. Can be positive, or negative. It just depends how we're going to choose our normal vector n, right? So depending on which normal vector we have chosen, which normal vector we have chosen. So why is that happening? Because we have two normal vectors, right? So we have two normal vectors. We have two normal vectors. One pointing in each direction of the surface. We have two-sided surface, right? So one pointing toward each side of the surface. Toward each side of a surface. All right, so let's look at the example. So example is like this. Compute the flux of the vector field and vector field is given by f, x, y, and z equal to x, y, and 0 over the portion of the paraboloid which is z equals to x squared plus y squared below z equals to 4. And we have to give the orientation or pick the orientation oriented with upward pointing normal vector. So in our case we have a paraboloid which is basically in each direction it has a parabola. If we go up, so something like this. Okay, and okay, so in each direction we have a parabola and we limit ourselves at z equals to 4. So we put the top on it at z equals to 4. So let's recall the normal vectors to a surface. Normal vector to a surface n can be found by calculating the partial with respect to f, partial with respect to y, and -1. That's the normal vector to the to the surface, but since we have two directions, we can use plus or minus. We can use plus or minus. And in our case, we're going to get partial with respect to f, z equals to f of xy we need, right? So partial with respect to x will be 2x, will be 2y, and negative 1. And in our problem, we need the normal vector pointing up. We need the normal vector pointing upward. And that means we need a positive z direction. We need a positive z component. So we have a negative one, we need a positive one. So let me not call it m, I'll call it m, because it's not a unit vector, it's just a normal vector, but we need a unit normal vector. So that means m in our case will be equal to negative 2x, 2y, negative 1. So it's going to be negative 2x, negative 2y, positive 1 if we distribute this minus through the vector. Now we need to construct a unit vector n. So n will be just a normalized m vector. Normalized m vector would be looking like this: 2x minus 2y, 1 divided by the the norm of m, or the magnitude of m, which is the square root of 4x squared plus 4y squared plus 1. All right, so let's look at our integral. Our integral is over s f dot n ds, f dot n ds. But we can also take ds and rewrite it. We can rewrite we can write ds as ds equals the magnitude of m times dA, which is the square root of 4x squared plus 4y squared plus 1 dA, right? And this way we can go and build our integral over s, which is f dot n ds, which is equal to integral over the region R, where we have vector f, and our vector f, as you remember, was x, y, and 0. So field is x, y, and 0 dot Then the normal vector, which is, we have it over here, which is negative 2x, negative 2y, and 1 divided by the square root of 4x squared plus 4y squared plus 1 times square root of 4x squared plus 4y squared plus 1 dA. And this vector we can divide, and we get a double integral over region R. And what is this region R? Our region R, if we look from the top, that's the projection, onto our xy plane, which will be a circle, of of radius 2, right? Y2, because we have z equals to 4 on top, so it's 4 equals to x squared plus y squared, so we need to take square root of 4 to get the radius. Alright, so we continue on. We have x, y, and 0 dot negative 2x, negative 2y, and 1 dA. So if we calculate this dot product, we have a integral over the region R. So x times negative 2x, it's going to be negative 2x squared. Y times negative 2y is negative 2y squared. 0 times 1 is 0. And so we have this integral over here. Alright, basically, since we have a circle, it's probably best way to go through the polar coordinates. Polar coordinates, we can factor this negative 2 out. Negative 2, we have x squared plus y squared dA. And now we switch to polar coordinates. So this is our radius squared for the x squared plus y squared. So we have radius squared, we have negative 2 up front, and dA becomes r dr d theta. So our r is changing from 0 to 2, and since we want to go the whole circle, our theta changes from 0 to 2 pi. And then it's just the matter of calculations. We're going to get negative 2 up front, r cubed, and we have a double integral from 0 to 2, from 0 to 2 pi, dr d theta, which is negative 2 r to the 4 over 4, from 0 to 2, and the integral goes from 0 to 2 pi d theta. So 2 and 4 we can divide, and we plug in 2 inside, and there's going to be 2 to the 4, which is 16 over 2, so it's going to be 8. So we have negative 8 integral from 0 to 2 pi d theta, which is negative 8 theta evaluated from 0 to 2 pi. So we get negative 16 pi minus 0, which is just negative 16 pi. Okay, so what do we do next? So next we're going to talk about heat flow heat flow. So to talk about heat flow, we need to, we're not going to dive deep into the physics, but we can derive the following. So heat flow across a surface, across a surface, across a surface. That's what we need to calculate. And the rule is the following. If T of x, y, and z, sorry, not vector, just the temperature, gives the temperature at x, y, and z, then the net heat flow, across a surface S is the flux of F, which is given by negative K times the gradient of T, where K is called the heat conductivity of the material. The heat conductivity of the material. So it's a constant. For each material you have the constant K. So let's look at the example. Our example will talk about this following T. So for T given by the following function, which is 30 minus 1 over 18 z squared, and constant K is equal to 2. We need to compute the heat flow out, of the region bounded by x squared plus y squared plus z squared equals to 9. So it's a sphere with radius 3. Alright, so how do we start? To start, we're going to calculate the flux of -2 gradient of the function t, which is 30 minus 1 over 18 z squared. But as you can see, there is no x component, there is no y component. Both derivatives will give you 0. And so we have -2, 0 for the x component, 0 for the y component. And for z component, it will be 2 over 18, which is -1 over 9 z. Okay, so we can distribute this number 2 through this vector. 0, 0, 2 over 9 z. Alright, so we calculated our flux, and since we have the flux, we can calculate the normal vector to a sphere. So normal vector n to a sphere. And to calculate the normal vector to a sphere, which we can calculate the gradient of the equation, right? So gradient of x squared plus y squared plus z squared. And we're going to get 2x, 2y, and 2z for the vector form, but it's not normalized, so we need to normalize it to get n. So n will be 2x, 2y, 2z divided by square root of 4x squared plus 4y squared plus 4z squared. All right. But since we have an equation of our square over here, x squared plus y squared plus z squared is equal to 9. So we know x squared plus y squared plus z squared is equal to 9. And if we take this idea over here and multiply both sides by 4, that would mean that 4x squared plus 4y squared plus 4z squared is equal to 36. And we can take this and plug it in over here. That would imply that square root of 4x squared plus 4y squared plus 4z squared is equal to square root of 36, which is 6. All right. And if we take this and calculate it, we're going to get 2x, 2y, 2z divided by 6. And if we simplify it, we're going to get 1/3. We take 2, we move it out, over 6, which is 1/3. X, y, and z, that's our normal vector n. So now we can calculate f dot n. And our vector f was 0, 0, 2 over 9. 0, 0, 2 over 9. This is vector f. Alright, so f dot n will be 0, 0, 2 over 9 z dot 1/3 x, y, and z. So 0 times x is 0, 0 times y is 0, so we have 1/3, and we have 2 over 9 z times z, which is 2 over 9, 0, 0, and 2 over 9 z squared. So finally we have 0, 0, 2 over 27 z squared. Okay. So we go in, we calculate the surface integral over S of f dot n ds, which is equal to integral over the region R. So we have I didn't do this one right over here, so should be 1/3. Didn't do it right, so it should be plus 0 plus this. Okay, and this should be just the answer. That's our dot product. So we put it over here, 2 over 27 z squared. Z squared, right? And here we put I'll keep s first and ds, s and ds. But so since we're talking about sphere, we would rather use spherical coordinates. Spherical coordinates. Spherical coordinates. All right, so for spherical coordinates, we have x equal to rho sine of phi sine of theta. We have y equals rho sine of phi, should be cosine of theta, sorry. Cosine of theta, and here should be sine of theta. And z is equal to rho cosine of phi. Rho cosine of phi. So for then in our rho is radius. Rho is radius of a sphere. Radius of a sphere. In our case, radius is equal to 3, right? Our sphere was x squared plus y squared plus z squared is equal to 9. So square root of 9 is 3. So that's our rho. So it's equal to 3. So in our case, it's 3 sine of phi cosine of theta, 3 sine of phi sine of theta, and the last one is 3 cosine of phi, which we can take and put over here for z. And we also need to calculate r phi cross r theta and calculate the magnitude of this vector. We've done this procedure a couple of times already, so I'm not going to do that, but if you take it and calculate it, you're going to get 9 sine of phi, 9 sine of phi. So again, we've done it a couple of times this semester. All right, so what does it mean for us? That means if we continue with our integral, then our integral is equal to double integral over region R. Then we have 2 over 27. We have z squared, and our z is 3 cosine of phi, so it's 3 cosine of phi squared. And times the magnitude of this cross product, which is 9 sine of phi, and we have d phi d theta. We have d phi d theta, and the only thing left is to talk about our region. And for our region, for phi we go 0 to pi because we're taking the full circle. That's for phi. And for the theta, we go full circle around on the bottom, 0 to 2 pi. Then we have 2 over 27 times 9 times cosine squared of phi times 9 times 9 sine of phi. Sine of phi d theta. Okay, what we need to calculate? This 9 and 27 gives us 3. Okay. And this 9 and this 3 gives us 3 over here. Finally, we have an integral from 0 to pi, 0 to 2 pi. We have 2 times 3, which is 6. We have cosine squared of phi, sine of phi, d phi, d theta. Okay, so how do we deal with this integral? Since we have cosine squared and we have 6, so 6 we can put outside. And then we have an integral from 0 to 2 pi. And over here we have an integral from 0 to pi of cosine squared of phi, sine of phi, d phi, d theta. So let's calculate this one on the side over here. So integral from cosine squared of phi, sine of phi, d phi, and the u will be the cosine of phi, and this tells you that du is equal to negative sine of phi d phi, which implies that if we solve for d phi, we're going to get du over negative sine of phi. So it's an integral of u squared sine of phi du over negative sine of phi. So sine and sine goes away. We have negative integral of u squared du, which is negative u cubed over 3. Alright, so we've done it on the side over here, and we move forward. And we say that our integral is equal to integral from 0 to 2 pi of negative u cubed. Oh, u was cosine of phi, so negative cosine cubed of phi over 3 evaluated from, and we have 6 over here, evaluated from 0 to pi d theta. So we plug in pi first. Cosine of pi is -1, and -1 cubed will give us -1, so minus and minus will go away, so we're going to get 6 integral from 0 to 2 pi. Alright, so we plug in pi, so it's 1 over 3 minus, and then when we plug in 0, and minus will be plus, so it's also going to be 1/3. Alright, d theta. And so we have 6 times 2/3 times theta evaluated from 0 to 2 pi. So we have 6 and 3 will give us 2, and we have 4 times 2 pi minus 0, which is 8 pi. And probably a good place to stop this lecture, and I'll see you in the next one.